Now that we have looked at how to set up for a titration, we want to know first of all how it's run, and secondly then what to do with the results that we get from a titration. So in this lesson what we're going to do is we're going to run through the procedures used for carrying out a titration, and then secondly, the second half of this lesson, we're going to learn how to use the information that we have gathered from the titration to work out the unknown concentration from the solution whose concentration is unknown. Okay, so we've reached this stage now where you're ready to go. You know how to deal with your conical flask, you know how to deal with your burette, you know how to deal with your pipette, you know how to deal with any other piece of glassware that is involved in carrying out a titration. Okay, so we've reached the moment where we're going to do one. So run the titration 3 times. So this is always the case in the lab. We only have an hour normally when we're in school to do this thing. So we run a titration 3 times. Okay, the first time we run a titration is in order to get a rough estimation of where the point of neutralization or end point of the chemical reaction is going to be. So we never take the first answer, the first titration figure, as part of our calculations. It is a guide. Okay, so you'll always have 3 attempts. So you'll have trial 1, trial 2, and trial 3. Now, the trial 1 is always just an approximation for where the end point is. So basically you're free to open the tap to allow the acid from the burette into the base as you continuously swirl the conical flask, and that's key. Okay, we talk about solutions in chemistry, but we should always think about solutions as being homogeneous. All right, and the way that we aid a solution becoming homogeneous is to swirl it. So as you open the tap of your burette, you swirl the conical flask. Okay, and you don't have to continuously swirl it and put it down, swirl it again. Okay, and also if you stop every maybe 15 centimeters or so and wash down the inside of the conical flask with water. Now you might say to yourself, are you not diluting the solution? Yes, you are. However, you have already via your pipette trapped a fixed number of moles. Okay, I want you to think of that. So when you pull up your 25 centimeters cubed and you discharge it into the conical flask, there are a set number of moles in there. Okay, that number of moles doesn't change no matter how much water you put in there. The molarity might change, but the number of moles won't change. So it's like the same thing as saying, you know, if you put 2 people into a bath or 2 people into a swimming pool, the concentration changes, but the number of people in both stays exactly the same. So if we put some moles of a chemical into a small amount of water, or the same number of moles into a large amount of water, it's the same number of moles. I need you to think about that. Okay, so we're free to wash the inside of the conical flask quite regularly, just to get all the reagents from the that stuck to the sides down to the bottom where they can react fully. So again, we open the tap, we allow in the acid from the burette until we get a color change. Now, normally for the first one, we're way off. So let's say, for example, we get 27.6 centimeters cubed. Okay, then we run the titration again. Now here's the thing, can I run the titration again without having to fill my burette? Can I get another 27 if I've already used up 27.6? The answer is no, because 27.6 is 55.2. So therefore we're gone way over the scope of the burette. So we would have to fill up in this case here. So I refill using my filter funnel, using my glass rod. I refill the burette and I get ready for my second trial. This time we have a guide number. So I can open the burette, let it in, swirl it round, get to about 20, 21, and then you begin to slow down, because these two have to be accurate. Okay, these have to be the accurate trials. So then we get to 25, we're going 26, we're getting to 27, and then we go drop by drop by drop. Now this is something you can only do when you have a burette in your hand, but the tap allows you to control the flow of the acid into the conical flask. So when we're approaching the point that we know is the point of neutralization, the color change of the indicator is going to take place, we slow down and we allow it in drop by drop. This time we get a reading of 27.3. Okay, now that's an awful lot more accurate. So what do we do? Run it again a third time to verify the second reading. Okay, so you run your titration a third time, you refill your burette, you then start your titration, and this time we get 27.2. Okay, now we can stop. And one of the key reasons why I can stop is because the readings here are within 0.1 of each other. So in other words, they're verifying that the end point, the point of neutralization, is in here. Okay, now I'm only allowed to take one reading. only one reading can come back into my formula. So how do I do that? Well, first of all, you never use the first one. The first one is only a guide, okay? That's all it is. So what do I do with the other two? How do I work out which one to use? The answer is you use neither. Unless, of course, they're both the same. You get the average of both, which will come out as being 27.25 centimeters cubed. And that is going to be the volume of acid that you will use in your V1M1 equals V2M2 formula. Okay, so that's how we run a titration. So we run it always 3 times in order to try and figure out where is this point of neutralization? Where is the end point of my chemical reaction? The first time we run it, it's a rough estimate. We get an idea. Then the second time, we approach that point carefully till we get a change in color. And then the third time, we try to verify the result of the second time by making sure that the results of the titration are very, very close together. We do not use the first reading, and we use the average of the second and the third. As I said to you already, say for example, after your titration, say the first reading was 12.3 centimeters cubed. Now, would I have to fill my burette up again? Would I have to take it down, fill it up and go through all that hassle? Or is there another 12.3 in there that I might be able to use? And the answer is yes. So you don't have to refill every time you want to do a burette trial, okay, or a titration trial. If you realize that you have enough liquid left in your burette to run a second trial, do so. Start at that point and move on, and then by subtraction you can work out the value. So you don't have to refill for every trial if there is enough liquid in the burette to do a second trial. Indeed, say you did the first one was 5, well then you could do all 3, because the maximum amount of liquid required is only 15 centimeters cubed. So therefore, always judge, do I have to refill the burette, or is there enough liquid left over to run a second or a third trial? Okay, that's the key thing. Okay, you do not, as we said, have to refill if there's enough reagent present in your burette to complete another cycle. Then start from the volume that is shown. Here's a key thing obviously people do. Okay, they're running a titration. The chemistry is happening in the conical flask, and they're up there looking at the water going down there, or the acid going down the burette. That's not where the chemistry is. The chemistry is in your conical flask. So when you're doing a titration, you are down at the tap, you're swirling the conical flask, you're adding in the acid, swirl, add in, swirl. You're watching the chemistry. You're not watching the numbers. You get the number at the end when you've reached the end point. So you have to focus on this. That's where the action is. You don't focus up here when you're running a titration because you'll miss the end point, okay? So you always focus down here on the conical flask when you're running a burette. So watch the chemistry, not the burette. And finally, swirl it every 10 centimeters. Swirl, stop the burette, swirl, and then make sure you rinse down the sides. Swirl, another 5, 10, swirl again, okay? So swirling makes sure the solution is homogeneous. There's no hot spots of concentrated chemical in there. It's all homogeneous. Now there's a video there that again I want you to watch yourselves. It'll take you through how to run a titration. It's extremely good. It goes into every detail of what you should be doing if you're running a titration. So you can pause now if you wish. You can click on that link on the slides and that'll bring you to the video and you can watch it. So if we're reading our burette, so we're down here, conical flask, we get a color change. All right, so we know the reaction is finished. Now I turn my attention to my burette and I've got to take the reading. And this is where people can make a big mistake, because first of all, the reading that you take has to be at eye level. You don't look up at the burette to see what number, nor do you look down. You have to take the reading at eye level, okay? So that might mean having to lift the burette down onto a stool or having to move up to see exactly where it is, but you must take it at eye level. And the key thing about it is that because usually in a burette, because it's made of glass, the liquid is U-shaped, like that. We don't read from the sides. We always read from the bottom. See that? So therefore, when we're looking at the value, we always read from the bottom of that U shape. And whatever number is over here, say 5.6, whatever it's going to be, that is the value that you take. Now I'm going to do a bit of practice on that. That's key, because you need to know how to do this well. So if we take this one here, I'm going to do this one with you, and then I'm going to leave you with 2 further ones to do yourself. Okay? Let's take this as 3 trials in a given titration. All right, and let's see exactly what type of readings we get from each of the 3 trials. Now, titration 1 has a starting point and a finishing point. Where am I starting? Well, first of all, we've got to try and figure out how many units are between 0 and 1. And the answer is 10. So therefore, each one of those units is 0.1. Okay, notice that the bottom of the U shape is between 4 and 5. hasn't even reached 0.5. So therefore I would suggest that you take that first reading as 0.45. Okay, now you can kind of get it to 0.1, but if it moves in between two of them, you have to guess the 100th position. We've no idea exactly what it is, but you can guess it. There's enough marks in there to be fairly accurate. Okay, and then that's the first one, and then the second one, the final reading is 27.123, bang on. So 27.3. So I come down here to my table. Titration 1, what was my initial reading? My initial reading was 0.45 centimeters cubed. What was my final reading? 27.3. So therefore, how much liquid did I actually use? Well, 27.3 minus 0.45 comes out as 26.85. Okay, now that's my guide. Okay, we won't ever be using that in the calculations, but it's a guide. So I move to titration 2 and I run it again, this time being very, very careful to try and mark the point of neutralization, the end point of the reaction. And here's the readings I get. This time we're starting off at 0.6 exactly. So 0.6. And we run the titration, and this time it comes out bang on 27. See that? Bang on 27. So therefore my initial reading was 0.6. My final reading was 27, which leaves me with 26.4. Okay, so you see the way it's becoming a little bit more accurate? And now the third one we try to use to verify the second one. Let's see what we have. Initial reading looks to be halfway between 1.12, halfway between 1.2 and 1.3, so 1.25. And then the final reading of this run again appears to be halfway between 27.7 and 8, so 27.75. Okay, so 27.75, and we start off at 1.25, and we end up getting, that's going to give me 50 there, and that's going to give me 26. Aha! Now look at these two. Notice how close they are. 26.4, 26.5. They are 0.1 of a centimeter cubed away from each other. That's enough. That's a good margin of error. We'll take that. And in order to combine these two results, we take their average as being 26.45. And that will be the average titration figure. So over here, the final average titer value is 26.45 centimeters cubed. Okay, now that's the example I'll do with you. I'm now going to leave you with a further two. This one, which you can now pause and do. And notice, by the way, before you pause anything, notice there's a proper U shape here. Okay, but do the same thing. Take the 3 trials and then fill in the table. And then this one, which again I'm going to ask you to do. Take the 3 trials, work out the initial and final readings, and see if you can get an average titration value. If you want to go over some burette readings again, take this link here from the slides they have provided, okay? And that'll bring you through reading, or it'll bring you through the meniscus and reading the values, just in case you need more practice. But if you follow these two, this one here, burette readings 1 and burette readings 2, by the time you've done the second one, you should be okay with them. Okay, and we'll revisit these in our live class anyway. So you've done your titration. You've carried out your 3 titrations. The first value has given you a good idea as to where the endpoint is. The second one has been accurate, and the third one has verified the second reading. Okay. So when you get your average titer, what are you going to do with it? Well, the answer is you're going to use it in your titration calculation. Okay. Now, what's the titration calculation? Well, first of all, it's a reaction. The initial ones, anyway, will be a reaction between an acid and a base, whatever they're going to be. You will be given a volume of an acid and a concentration of an acid, or the volume of a base and the concentration of the base. One of the solutions given will have both numbers, the volume and the concentration. The other solution, you'll only have a volume. You won't know the concentration, and that's what we want to work out. Okay. Now, if it's a case that your acid and your base react with one another in a ratio of 1:1, then work out the number of moles of the acid and set it equal to the number of moles of base. And in there, you'll have one little x that you've got to solve for. That's the easiest way. Okay. If, for example, you have an acid and a base that react in the ratio of 1:2, let's say. Okay, well then you still have to work out the number of moles of acid, you still try to work out the number of moles of base, but this time, because their ratios are not the same, you can divide the respective moles by that coefficient. Now keep that in mind. So you'd end up with something like that. So it's still the same formula there and there. It's just when there's not an equal ratio between the reactants, we've got to take that into consideration by dividing the number of moles by those coefficients, just to make sure that we're able to equalize the moles on both sides. Now, let's take a look at the notes here. The balanced equation is crucial to the solution of any titration question, as it reveals the ratio of reaction between the two reagents. So for example, HCl plus NaOH. What do you notice? 1:1. H2SO4 and 2NaOH. What's that? That's 1:2. Okay, so watch very carefully as to what the ratio of reaction, what are the coefficients in front of all of these substances, 1:1 or 1:2, and take that into consideration. If it's 1:1, then you just use V1M1 equals V2M2. But if it's 1:2 or 2:3 or 3:7 or whatever else, then you've got to put them in as the bottom divisors underneath the V1M1 and the V2M2. Okay, write down V1 and M1. Now, always begin with the substance whose volume and molarity are known. Because if they give you the volume and molarity, you can calculate the number of moles immediately. Okay, in the second reagent, you'll know the volume, but you won't know the number of moles. So you just simply call the number of moles X. And then you've got an equation in X that you can solve. Write down V2 and M2, which is the volume and the concentration of the second reagent. And then, if there is an unequal ratio between N1 and N2, write them down. Okay, so that's the first thing we're doing. We're gathering information. What does the balanced equation tell me? What's the volume and the molarity of the standard solution? What's the volume and the molarity of the solution's concentration I want to find? And how do they react together from the balanced equation? What's the ratio of reaction between these two? So the best thing to do, just to go through this very quickly again, we said is the V1M1 is divided by the ratio of coefficients if they're not 1:1. We know that. So that's what you end up with. The number of moles of the acid, the number of moles of the base, divided by the coefficient of the acid and the coefficient of the base, should they not be 1:1. If they are 1:1, then you don't need them. Okay, so just keep that in mind. Okay, best thing to do, let's take an example. I'm going to do 2 examples, and then I'm going to leave you with 3 to do yourselves. So the first one here, after my titration, this is what I've discovered. It takes 83 centimeters cubed. Now, I have a great habit when I'm reading questions like this to write down above them V1, M1. So that's the first volume, V1. Of a 0.45 molar, well, that's the first molarity. To neutralize 235, there's my second volume of a HCl solution. Oh, no mention of its concentration. The balanced equation for the reaction is, good, what is the concentration? So that's going to be my this will be my M2. Okay, let me just write that down properly. I really don't like making mistakes in this thing. It annoys me. So that's my M2. Okay, so straight away, I know everything about the base. So I write down from the balanced equation, NaOH and HCl. The volume and the molarity of both of those, what are they? 0.083 litres for the volume, because don't forget, work in litres. Please always work in litres. And the molarity, 0.45. What about the HCl? What does it have? It has a volume, the second volume, of 0.235 litres, and its molarity is not known. Now, do I need an N1 and an N2? Check. What's the ratio of reaction? The ratio of reaction is 1:1. So there's one of them and one of them, which means I do not need N1 and N2. So the very simple thing I do is 0.083 multiplied by 0.45 is exactly the same as 0.235 by x. And in order to get x on its own, you divide both sides by 0.235. They'll cancel, leaving you with x equals 2, and then you simply take those two, or that fraction, the numerator and denominator as they are, put them onto your calculator, 0.083 multiplied by 0.45 divided by 0.235, and the answer in decimal form comes out as 0.1589. Now look, 1589, I'd say it's okay to say that. That is the molarity of your HCl. Quite simple. Now you might say, yeah, fine, V1M1, V2M2, that's grand. What happens when the ratio is not 1:1? Well, let's take a question in relation to that, the second work example. It takes 38 centimeters cubed of a 0.75 molar solution NaOH to completely neutralize 155 centimeters cubed of a sulfuric acid solution. The balanced equation for the reaction is, as given, and what is the concentration of the H2SO4 solution? Again, do you notice? V1, M1. Over here, V2, M2. So what are we reacting? 2NaOH and H2SO4. So write down first of all, what about the NaOH? It's 0.038 litres, that's V1. What about M1? 0.75. What about the acid, V2 and M2? The volume of the acid, 0.155 litres. And what about the molarity of the acid? We don't know, it's X. Now, before we do anything else, check the ratio of reaction. Because the ratio of reaction, in this case, and you can see it very clearly, is 2:1. See that? So therefore, you do have to use N1 and N2. They have to be used in this calculation. So now we've got V1, M1, N1, V2, M2, and N2. So all we've got to do now is bring those figures up. Oh, sorry, did that again. I wiped off the wrong one. Can I get them back? No, we can't. Okay, let's do it again. What have we got? We've got V1. I'll work with this equation up here. So I've got V1, M1, N1, and V2, M2, N2. Okay, first volume, 0.038. First molarity, 0.75. The number in front of the NaOH is equal to 2. V2, the volume, 0.155 litres. The molarity we do not know, and the number in front of it in the balance equation, 1. Okay, so now still do your V1M1. V1M1 equals V2M2. However, because we have to use N1 and N2, they now go into the equation as well. So we get 0.038 multiplied by 0.75 over 2 is equal to 0.155 times x over 1. And in order to get x on its own, what am I going to do? I'm going to divide by 0.155. That's what I'm going to do. Divide both sides by 0.155. Watch. If I divide both sides by 0.155, it'll cancel here. So I get x is equal to 0.038 multiplied by 0.75 over 2 times 0.155. So another way to say is bring that 0.155 from the top right down to the bottom left. Okay, just cross it diagonally downwards beside the 2. Then get out your trusty calculator and let's find out what this is. So turn on your fraction and you get 0.038 multiplied by 0.75 to be divided by 2 times 0.155. And when I press equals there, I end up getting, in decimal form, 0.091. So 0.092 moles per litre, or molar solution. Moles per litre, or moles, whatever you want to do yourself. That's it. That is as difficult as titration calculations get. Okay, now I've got 3 that I want you to try. So this one here, I'll just work on that. Same thing exactly as before. This one and this one. And I will take these questions up when we go back to the online class if you have any difficulties with them. They are quite straightforward. By right, you shouldn't have a difficulty with them, but you just might have missed something that you need a bit of help with. In the meantime, before the live class, if you need anything on this, the best thing to do is to ask. Send me an email, ask me to go through it with you, and I can send you back a video solution, no problem. So let me just go back over these again for you. So we've done that one. So this one, you can pause now and do that. This one, pause and do that. This one, pause and do that. We will then move on to the very final part of this particular chapter, which is running your own titration virtually online. Okay, so as soon as we master the calculations, we'll try a titration online just to give you an idea as to what actually happens visually, as well as being able to read the solution from the burette.